This lesson is on average and instantaneous rates of change. And rates of change are things like velocity, because that could be measured in meters per second or kilometers per hour, miles per hour. It's a unit of measurement over a unit of time. So it's not only just distances, it could be something like gallons per second or liters per hour, where you have something being measured over a certain amount of time. And in this class we're going to use velocity a lot because it's an easy example. So average rate of change, what is that exactly? Well, if I have a graph, and this function could be, a certain distance over a certain time, but it is actually, if I look at this point to this point, the average rate of change would be the slope of the line between those 2 points. And so if you think about that point is an x value of an a and a y value of whatever that output is, f of a. This other point is an x value of b, and then its y value is the output at b, whatever that is. And so if we're doing slope, that slope formula would be y minus y, or f of b minus f of a, over b minus a, the x minus x. Okay, this line between these 2 points is called the secant line. So you also need to know that this is the slope of the secant line between a and b. Okay, so the slope of that line is your average rate of change. Now, this might be something like if you were going on a trip and you wanted to know what kind of gas mileage your car was getting, and you could reset your mileage tracker and keep up with how many gallons that you filled up with, then you could figure out at the end of that trip how many total gallons you used and that total distance that you traveled. You would be calculating your average rate of change in gallons per mile. So that would be a real-world example. Instantaneous rate of change, that is at a split second, and that happens to be the slope of the tangent line at that point. The reference to your car here would be if I wanted to know the speed you were going at 9:52 and 3 seconds in the morning. So that is something that you would have to look at your speedometer to measure. And we are lucky to have that in our car, obviously, to know exactly what speed we're going at that particular time. On a graph, though, we don't have a speedometer. What we have to use is the slope of the tangent line, and I always draw just a very small tangent line to the best of my ability. That one might be a little bit flat, but we are looking at that tangent line to that point, and it's the slope, that's the most important thing, the slope of that tangent line. Okay, so now on your paper I want you to write the derivative is the slope of the tangent line, because this is something that is going to answer your questions in the future when you are doing problems and you are stuck. It is the most basic idea, but people tend to forget it because they get wrapped up in numbers. The derivative, which we are going to be working a lot with, is the slope of the tangent line. Please put that really big so that you can look back at it and jog your memory and have a starting place sometime. Okay, now I have a couple of examples of kind of what you're going to be doing today, and that is basing everything off this graph. I'm using distance and time because, like I said, velocity is the easiest thing to reference because you kind of understand it. And again, this is a distance and time graph, so if you thought about the slope that you would be getting, your y's over your x's, they are distance over time. And so distance over time, that change in distance and change in time, is average velocity. Velocity is again, a rate of change. This is just one example of a real-world situation. But we have this graph here, and I have, it's kind of like a piecewise function that's been pieced together, but we're going to answer some questions about it. First, we're going to find the average velocity between time 0 and time 3. And so average velocity is just the slope of that secant line. I can just find it with the points. At time 0, you're at 1, so you have the point 0, 1. At time 3, you're at 2, so you have the point 0, or excuse me, at 3, 2. And then your average velocity will be the slope between those, so y minus y over x minus x is going to give you 1/3. And since we know that our distance is in meters and our time is in seconds, we know this unit would be meters per second. Okay, second question, estimate the instantaneous velocity at x equals 1/2. 1/2 would be about right here, so on the graph we're right here. And since it's on a line, we can actually estimate that tangent, that slope, really well. It looks like you're going up 1 and over 1, so it looks like a slope of 1. So my estimate for the instantaneous velocity, or the slope of this tangent line, is about 1 meter per second. I can't be sure of that because it's not exact, and you'll come up with some graphs where you really are estimating, but it's our best guess. All right, what about at 2? What's our instantaneous velocity? And at 2, we are on a horizontal line, and that one we can know. The tangent to that, obviously, still flat. The slope of a flat line is 0, so 0 meters per second, and that makes sense because if you're at that same distance between time 1 and time 3, you haven't moved, so you don't have a speed. It's 0 meters per second. Alright, now the number 4 is going to be the challenge, is sketching the velocity versus time graph. So it's actually thinking about all the slopes that you encounter. So I'm going to write those in blue so I can think about them correctly. Between 0 and 1, we thought about that slope as being 1 because it looked like up 1 and over 1. Between 1 and 3, that was a slope of 0. Between 3 and 4, it went from 0 to a very steep slope, and that would mean a higher number when we're plotting velocity. This is probably one of the hardest things to wrap your brain around, and it's going to take some time. Take one piece at a time. But again, you're looking at this graph and thinking about what the number for the slope, but you're going to be plotting that number down here as a y value. Okay, this is going to take practice. Okay, so I'm going to have my sketch here, and again, this velocity is in meters per second because our original graph was in meters and seconds. Our time is still in seconds because our time is an independent value. And let's scroll back up, and again, the first part between 0 and 1 had a slope of 1. That means between 0 and 1, I have a y value of 1 on this graph. Okay, then we go back up. Between 1 and 3, it was flat. It has a slope of 0. And it jumped on that corner. It jumped from having a slope of 1 to a slope of 0. It wasn't a smooth transition. It's supposed to connect, but you know how things work for me sometimes. So it's not a smooth transition. It truly jumps from a slope of 1 to a slope of 0. So our y values down here need to jump from a slope of 1, or from a y value of 1 to a y value of 0. And I'm going to put an open circle on both of those because something I'll talk about in just one second. And let's plot 0 until we get to 3. Now, why am I putting open circles? If you remember when we were sketching tangent lines, a sharp corner has so many different tangent lines that you can draw that it's an infinitely many. So it's not an actual slope that we can plot there. That is a point where you cannot do a tangent line. So those are open circles down here. Alright, the last part, the part between 3 and 4, is going to be the hardest here. And I need you to think about little bitty tangent lines, drawing those in. If I start here, this this one that I've drawn right next to 3 is almost flat, but it's starting to be positive. Then as I move on, I get steeper and steeper, which, we looked at maybe slopes of 1 or slopes of 1.5 and then slopes of 2. And then as I go to 4, this slope might be a 3 or a 4. It's very steep. So I need to rise with my numbers between 3 and 4 very smoothly. And so right after 3 is when we start becoming positive, and by the time we get to 4, we're way up here in our y values because those slopes had gotten very steep. And so this is going to rise smoothly, but it's going to be connected. And there aren't any open circles because there aren't any sharp corners. Like I said, if you're not getting this, give yourself some time. Take a piece by piece. But it's very hard to look at one graph and think about a graph that's related to it and not draw that same graph. So again, you have to think about slopes on the original graph, y values on this graph. And we will have plenty of practice with this. That concludes this lesson.